Dear students, in physics, let's see another experiment now. This is from the section Waves and Oscillation. What we are going to see here, verification of the relationship between the frequency of a stretched string and its vibrating length using the sonometer, right? Frequency and the length, how that is connected on a stretched string. We are going to use the sonometer. I will show you the sonometer. How the length and the frequency are connected is what we are going to see, right? You know, this is what we are going to do. I'll tell you the plan. Sonometer will look like this with a string on it. Which will have two bridges, and the string will be attached this side, right? There are two types of arrangements. One, you can connect the string to two nails on both sides, two screws on both sides. If not, on one side you can attach a pulley, and over the pulley you can bring the string and you can connect a weight on it. If you want to change the tension, maybe that arrangement is good, where the string one side is fixed, the other side goes over a pulley and it carries a weight. So, you change the weight, then the tension will change in the spring. If you are not planning to change the tension, then you can keep it at one particular tension itself, then you can fix it both sides. Couple of things. The velocity equals f lambda, v equals f lambda. How we are going to find the lambda here? We will take a tuning fork, tuning fork in this shape. Tuning fork with a known frequency. Usually tuning fork, on it they would have printed the frequency of it. So, we will take a tuning fork with a known frequency, let it vibrate, give a vibration to it and hold it here. Hold it here means you have to keep it such that the base of this touches the box, sonometer box. So, when this vibrates, the energy will be transferred to all the particles in the sonometer. So, sonometer, the string on it, the air molecules within the sonometer, everything will be vibrating, right? When everything is vibrating, now see, this is going to have a frequency depending on the length. So, what we will do, I am trying to find the length at which this string gets a resonance with this tuning fork, right? This f, the natural frequency of this string, that changes with the length of the string. How do we adjust the string? The bridges will be movable. Sometimes one bridge will be fixed, one bridge will be movable. Sometimes both bridges will be movable. So, what we will do when we are starting the experiment, we will keep the bridges too close, so that this length is too less. The length that is vibrating will be too less. Then little by little you keep increasing, having this tuning fork being vibrated and kept on the sonometer, holding it, you slowly increase the vibrating length of the string. So, usually we do not adjust one bridge, because you need one hand to hold the sonometer. With the other hand, increase the gap between the two bridges by moving one bridge away. Little by little you move one bridge so that the length increases. At one point, the natural frequency of that string within that length and this frequency of the tuning fork will become equal. Then the resonance will happen. How do we understand the resonance happens? We take a small piece of paper or tissue and put it on it here, small piece, right? We call it the paper runner or a small piece of paper. Just fold it and keep it on it. So, when you vibrate and keep this tuning fork on the sonometer, this paper will be vibrating slowly because the energy is being transferred to that paper as well, paper piece as well, paper runner. But when resonance happens, maximum energy is going to be transferred from the tuning fork to the string because the frequencies are same and the resonance is taking place. So, since more energy is being transferred, the vibration will happen on the string with maximum amplitude, with high amplitude. Why? It gets more energy at resonance. We studied that when the resonance happens from the source to the other particle that resonates, more energy will be passed. Then the string will vibrate with more amplitude, which means this paper runner will be thrown out from this. So, the experimental procedure is, after you vibrate this tuning fork, you keep it on the sonometer, slowly increase the gap between the bridges. At one point, the paper runner will be thrown out. When the paper runner is thrown out, you know resonance has taken place, right? So, let us say when the resonance takes place, this is how the bridges are, then you know this L, and the frequency for this L must be as same as of this of the tuning fork. Then only the resonance takes place. So, we know the frequency now. We know the frequency. V is a constant as long as you don't change the string tension, because V is square root of T over M. T is the tension on the string. M is the mass of the string for unit length. 1 meter length. How much is the mass of it? Mass per unit length is M. Mass per unit length doesn't change, but tension can be changed. We are doing this experiment under constant tension, which means V is a constant. This is a constant. Since T is constant, tension is constant, velocity is going to be constant. How do we get lambda? When the resonance takes place, the standing wave would be like this. If this is the string, this is how you are going to get the standing wave. This is how you are going to get the standing wave. So, if we can measure this length between the two bridges, that is going to be lambda by 2, right? Because this is half the string you have, lambda by 2, Then lambda will be equal to 2L. That way you can get lambda, right? So, you get V equals F into 2L, Now, L is going to be V by 2 into 1 over F. Since V is a constant, we can say L is proportionate to 1 over F. L is proportionate to 1 over F. Clear? This is the relationship between the length and the frequency. So, you must understand, when the length increases, the frequency of the string, natural frequency of the string reduces. Right? So, imagine when I use 512 hertz tuning fork, and if the resonance takes place at L equals, let's say 40 centimeter, just assume, then when you use a lower frequency, let's say you use 480 hertz, this L has to be more than 40 centimeter now. Why? Frequency reduces, then 1 over F will increase, L has to increase. Frequency and length are inversely proportionate. When frequency reduces, L increases. Clear? This is the relationship we expect. So, what we are going to do? We will take multiple frequencies. For each frequency, we will find the length at which the resonance takes place, right? We will draw the graph L versus 1 over F. If we get a straight line, then straight line through origin, right? If you get a straight line through origin, then it's going to be proven. L and F are inversely proportionate. It will be proven, right? Let's see how to do it. Now, let's see another experiment in physics in the section mechanics. What we are going to do here, we are going to arrange a pendulum, simple pendulum, and using the pendulum, we are going to find the gravitational acceleration. We usually mark it as G, gravitational acceleration G, simple G, and the value of that we always take it as 9.8 or 10 meter per second squared. that we already know the value and we use that in calculations, but how to derive that value experimentally is what we are going to see now, right. So, look at this, when I say pendulum, a string and a small ball here, right. What do? You give a small displacement horizontally, then it will start oscillating. How does it oscillate? Let me show it to you. Right, it oscillates like this by a small angle. Small angle. Huh? Don't oscillate it by like 30-40 degrees, must be like 5, 6, 7 degrees in that range. A small oscillation, small displacement has to be given by the time for one full oscillation. One full oscillation means, see, it starts from here, it goes up to here and then return and again it goes up. So, starting from 1, 2, 3, coming back here 4. 1, 2, 3, 4 is what you call one full oscillation. From the middle it goes to the right side, comes back to the left side, again it goes to the middle, that is one full oscillation we say. And the time for that oscillation t is given by 2 pi square root of L over G. 2 pi square root of L over G. L is the length of pendulum, G is the gravitational acceleration that we want to find. So, it is very simple, you can see, you measure the length and let it oscillate and find the time for oscillation. T is known, L is known, you can find G. But in physics, we usually go for the graphical method. So, if you are going to use a graphical method, what do? Square this, T squared, 2 pi getting squared, it will be 4 pi squared. The G comes out and L also comes out. Y M X. We are going to change the length of this pendulum to multiple different values, one by one. You change it, maybe like take 50 centimeter, 100 centimeter, 150 centimeter, likewise take different lengths and measure the time and draw the graph T squared versus L. T squared versus L, the gradient of that graph has to give you 4 pi squared over G. Then G will be 4 pi squared over gradient. This is what we are going to do, right? Simple. Few things that you have to note here. One, when you measure L, the length has to be measured from the center of this ball, because pendulum, not only the string, even maybe if you know the length of the string, then you have to add the radius of this ball, so that will be the total length. That is what we mark as L. Basically, length has to be measured from the center of gravity of the ball that we use here. Since we usually use a uniform sphere, you can take the center as the center of gravity, right. So, with the length of string, radius of that ball has to be added to find the total length of pendulum, point number 1. Point number 2, okay, how are we going to fix this on the top? If you take a stand and if you fix it with the clamp of the stand, let us say it is going to be something like this, right. Say this is your stand, then you have a clamp here, right. Here if I hang this, what will happen? Let me show you the view from this side. If I look it from this side, how it will look like. This clamp will have a shape. Let us say it has a shape like cross section is circular and the string will come like this, right. Now, let us consider different positions when it swings. when it swings, okay, this is one position. This is another position, right? So, the apparatus required for this experiment, mainly you can see this is the main apparatus on this in this experiment. This is what we call sonometer. Sonometer. Look at the parts of this sonometer. There is a string. Can you see attached here? It goes all the way up to here, right? This is a string. To connect this string, there are two ways, because we want to keep this string stretched. It has to be a stretched string. So, how we maintain it a stretched string? One end is always fixed here. See, one end is fixed here. One end is fixed here. One end is fixed here. And the other end, you can see it goes all the way. And the other end, now it has been fixed on this knob, right? If I want to change the tension on this string, I can rotate this knob. I can rotate this, right? One side, if I rotate this, the tension increases. The other side, if I rotate it, the tension decreases. But I wouldn't know exactly how much is the tension, I don't know. If you want to measure the tension also, then what do? You take the string and don't tie it on this knob, right? Take it above this pulley. There is a pulley here. Can you see? A pulley. So, take this string above this pulley and you can hang some weight here, right? Take this string above this pulley and you can hang the weight. Let us say you are hanging say 2 kilograms of weight. Then you know the tension on the string is going to be 2 into gravitational acceleration, which is usually taken as 10. 20 Newton will be the tension on the string. If you want to increase it, you can put another kilogram, so it becomes 30 Newton. Another kilogram, 40 Newton. So, if you want to know how much of tension is there on the string, then you can use the pulley setup. Here, I am not going to change the tension, I am going to do the whole experiment at a particular level of tension only. I do not even have to know how much the tension it is. Therefore, I am not measuring the tension. So, I do not need the pulley setup, I have just fixed it to the knob itself, right. That is one. Then you can see, this is what we call the bridges, right. The bridges in this sonometer that I am using, both bridges I can move. Can you see? All what we want is the gap between the bridges we should be able to adjust. In some sonometers, one side of the bridge, one part of the bridge might be fixed. Then you will be able to move only one side of the bridge. But here the sonometer I am using, both sides of the bridge I can move it. Okay. However, whether it is both movable or whether it is only one movable, whatever, what we are trying to do by moving this bridge is to change the gap or the length between the two bridges, right. And you have this sonometer surface here, right. And under that you can have, you have kind of a cubic kind of arrangement. Can you see here? There is a cubic. So, what will happen? Listen carefully. I will take one of these tuning forks, right. This is what we call tuning forks. So, we will take these tuning forks, we will make them vibrate. How do we make them vibrate? We can use this rubber hammer. Using that, we can give a knock on that, so it starts vibrating. And the vibrating tuning fork will be kept on the surface here. We will keep it here, right, on the surface. Then what will happen? When the tuning fork is vibrating, it has energy, right. There is a lot of kinetic energy when it vibrates. So, when you keep that here on this surface,
that kinetic energy will be transferred to this sonometer. Then all the particles of this sonometer will start vibrating. Simple example, if there is a bus, when you start the engine, only the engine has to vibrate, right? But the whole body of the bus vibrates, isn't it? So what happens there? The vibration of engine is passed on to all other parts of the bus as well, right? Because the engine is connected to all the parts, physically it's connected to the parts of the body. When engine vibrates, the whole bus body starts to vibrate. If you are sitting in the bus, you will also be vibrating. Same concept here. I vibrate, I give a vibration to this tuning fork, keep it here. That vibration gets transferred to the whole sonometer. Because of that, this surface will start vibrating. We may not be able to see that. And within this box, sonometer box, there is a lot of air in that. So the air molecules, air particles, they start vibrating and they make a noise. They make a sound. They make a sound. I will be able to hear that sound through these two holes. You can see there are two holes here. We will be able to hear that sound through these holes, right? This is the setup of many musical instruments as well, like guitar. What happens when you start playing the guitar, not the electric guitar I am talking about, then the air within the guitar bass or the guitar box, that starts vibrating and you hear music from that. A similar setup is here in the sonometer. It's a very simple version of that, right? So that's what the sonometer is. And then these are the tuning forks. Tuning forks, I have different tuning forks because they are different frequency, right? Usually shorter ones have higher frequency. See, this is shorter. Look at the vibrating part of it, this is shorter. So it has higher frequency. Longer one will have lower frequency. If you compare these, this is of 256 hertz. That's the frequency of this one, 256 hertz. Whereas this one is 481 hertz. Let me check. 426 hertz, 426 hertz, right? So this is the longer one which has 256 hertz. When the length reduces, the frequency also increases. That's why when people have different voice. Some people have very thick voice. Some people have very, very thin, husky voice. That is partially because of the length of their vocal cord. Usually, females have shorter vocal cord. Then what happens? Their frequency, the vocal cord's frequency will be high. Because of that, the voice of females are slightly different from that of men. Right. So, length of the vibrating object and its frequency are connected. When the length of vibrating object reduces, frequency increases usually, right. And you can see there are some pieces of paper we have here. We call them paper riders, right, small piece of paper, but in the exam if you write it as small piece of paper, you don't get the marks, you have to write it as paper rider. What do we use this paper rider for? Look at this. I will take one paper rider and I will keep it on the string like this, right. Then I will keep these two bridges very close, okay. I will take one of the tuning forks, I will start vibrating them, I will keep it here. So when I keep it here, it transfers the energy to the sonometer, everything in the sonometer start vibrating. Same thing happens to this string as well. Then I will slowly increase this width. What will happen? At some point, the frequency of this sonometer, frequency of this tuning fork will become equal. In other words, frequency of the tuning fork and the frequency at which this string is vibrating will become equal. At that point, the resonance will happen. You know, when resonance happens, you would have studied in theory, when resonance happens, the energy transfer will be maximum. That means more energy will be transferred from the tuning fork to the particles in the sonometer. then what will happen? You can observe two things there. Point number one, the string will start vibrating with higher amplitude. You won't be able to see higher amplitude, but to observe the higher amplitude phenomenon, we are keeping this paper rider. Because when the amplitude increases, this paper rider will be thrown out of it. It will not be able to hold on to it, because when the amplitude increases, it will be thrown out. So to see where that amplitude goes to maximum, where the resonance, only when resonance happens, that happens. Before that, the energy transfer will be much less. Only at the point of resonance, the energy transfer is going to be maximum. Energy transfer from tuning fork to the particles and then the body of this sonometer. So to see at what point the amplitude of this vibrating string is maximum, we use this paper rider. So I told you there are two things that you can observe when the resonance happens. One is this paper rider will be thrown out. Paper rider will be thrown out. Second observation you can have, when I give the vibration and keep it here, since the energy is transferred to the body, and that the energy will be transferred to the air molecules within this box, the air molecules will start vibrating, and that will make a sound. So you will hear that sound, a humming sound you can hear. That humming sound will be maximum when resonance happens. Because when resonance happens, highest amount of energy is transferred to the sonometer, so that the air molecules also, air particles also vibrate with the highest amplitude. So when they vibrate with highest amplitude, the sound generated by those air molecules or air particles will be high. So those are the two observations you can have. One, when the resonance happens, this paper rider will be thrown out. Two, you can hear maximum sound from this sonometer. And when the resonance happens, when this paper is being thrown out, then when the paper rider is being thrown out, then we can see, let's say at this distance the paper rider is being thrown out, then if that is the first one you are listening, like say I'm starting from the closest distance, and then I keep increasing for a particular frequency, let's say for 256 Hertz. At this point, if the paper is being thrown out, that's the first note, or that's a fundamental note we call it. That's a fundamental note. That's the first time you are hearing that, right? So that will be the fundamental note. Fundamental note means in between these two, you have half of a wavelength. You have half of a wavelength. Which means if you measure this gap, lambda by 2. And the frequency is same as the frequency of tuning fork. When the resonance happens, frequencies are equal. So the frequency, the lambda by 2. If you know lambda by 2, lambda as well, right? You multiply by 2, you get lambda. So frequency, lambda, you multiply, you can find the speed of wave. So that is what we are going to do. Then why do we need multiple tuning forks here? We don't want to do with one tuning fork only. We are going to go for a graphical method. So we will take 5 different frequencies, 5 different tuning forks, each with different frequency. For each of them, we will measure this length and we will go for a graphical method. We will be drawing a graph L versus 1 over F. L is the gap between these bridges when the resonance happens. F is the frequency. So L versus 1 over F graph, that will be a y equals mx graph. From the gradient, we can find the velocity of the wave through this string. Right? This is what the concept and the apparatus that we are going to use in this experiment. Let's start doing it. Let's see that also you need to understand, okay, you have from the highest frequency to lowest frequency. We usually start with the highest frequency because, see, we keep it here. When the frequency is high, wavelength is short because f lambda is the speed. F is high, lambda is short. So you take the highest frequency, and if you are talking about the fundamental note or fundamental overtone or fundamental note, then for the highest frequency, you will have the shortest fundamental note. From this, the next one, let's say you are starting with 426. Let's say it's here. The resonance happens here. Then when you use another one which is lower frequency, let's say 380 frequency, 380 hertz, then the lambda has to be bigger, then you can go a little bit outside. Then you take another one, let's say 340, you go a little bit further. That's how it goes. Right? If you randomly start from anywhere, then you can't ensure what you are getting, the resonance that you get is for the fundamental note. You can't ensure that. It can be the first overtone, it can be the second overtone, we don't know. So to ensure it's a fundamental note that you are observing, what we do, we keep it very close, we keep it closest, and the highest frequency is taken first, find the fundamental tone for the fundamental overtone for that, and from that, for each lower frequency, you keep widening it, so that you can ensure for each of those frequencies, what you get is the fundamental note, not first overtone, second overtone or anything after that. Understand? So that's what you're going to do. Let me take the highest frequency I have here. I have 426 as the highest frequency. Let me start doing the experiment with 426 hertz. Right. Let me keep another paper rider here. You can keep any number of paper riders. Let me keep 2 paper riders so that I can easily observe it. Right. I've kept 2 paper riders there. I kept this distance very short. Let me take the highest frequency now, which is 426.6 hertz. Let me give a vibration to it. Look at this. You can hear that sound. That's because all those air particles are vibrating. All this sonometer body is vibrating. You hear that sound. But observe the paper rider. Nothing happens to the paper rider, which means it's not the resonance. It's not the resonance. Let me increase this distance. I'm just keeping this fixed. I'm keeping this side of the bridge fixed. I'm moving only this one. I'm moving only this one, right? Still no change on the paper rider. Still no change on the paper rider. Observe again. No change. No change. Let me increase it little by little. There is no change. Look at this again. No change. Small vibration is there, but still that's not the maximum. Let's increase this further. When you are increasing it further, when you increase the gap, make sure you keep these paper riders in the middle. Then only they'll get the amplitude. Yeah. Still not the maximum. Still not the maximum. Let's increase it further. You can see it vibrates, but not to the level of, being thrown out. See, it has reduced now. It has reduced now. See, earlier when it was here, let's double check. Can you see it has more vibration? It has more vibration. Yes. Seems like that's the maximum vibration we get. Let's keep it in the middle again. Can you see what happens to the paper riders? It vibrates. Let me increase a little bit more and see. Let me try it once again. Can you see it vibrates? Let me increase it a little bit more and see what happens. Keep it in the middle, then only they will experience the amplitude. No, it has reduced. It has reduced. See? No, previously it was more. Let me bring it closer again. Let me bring it more closer. Seems like that's the maximum we are getting. Look at this again. Let me keep it in the middle. That's the maximum vibration we are getting. You can see that. That's the maximum. Actually, this paper rider has to be thrown out. But when I use very high frequency, what happens? The wavelength is very short. Right? This is half of the wavelength. So when the wavelength is very short, you won't get very high amplitudes. The amplitude also will be minimized. Since the amplitude is less, the paper rider is not being thrown out. When I reduce the frequency, now this is at 426, I will be doing at 256 for the fifth reading. When we reduce the frequency, you can see this observation of the paper rider being thrown out very easily. Right. So for the exam, you can't write the paper rider starts vibrating more, not really. It has to be the paper rider being thrown out. Right. So here the energy is not that enough to throw it out. You can see it vibrates. It vibrates. You can see it vibrates. A high level of vibration is there. Can you see again? Once more. Keep it in the middle. A high level of vibration is there, but that's not sufficient to throw it out. Yes. So that's the point I can say the resonance happens. You saw that when the length was shorter than this, the resonance did not happen. The paper riders did not vibrate this much. When the length was more than this, it did not vibrate this much. This is the point where it gets that much of energy, which means the highest energy is transferred at this length, which means the resonance happens at this point. Let me get the readings now. See, this side of the bridge is at 53 centimeter, 53, yes, and this is kept at 41 centimeters, 41 centimeters. So 53, 41, we get a difference of 12 centimeter. That's what I measure as L. L is 12 centimeter. When I use a frequency of 426.6 hertz, 426.6 hertz, the L is 12 centimeter. 53, 41 on this side, 53, 41, and the difference is 12 centimeters. Right? Now what we will do, let's do it for the next frequency lower than this. This is at 426. Let me keep it. The next one I have, the tuning fork I have is at 384 hertz, 384 hertz. Right? So you understand, when I increase the frequency, the wavelength has to, when I reduce the frequency, wavelength has to increase. F lambda has to be constant, which means I can expect the resonance to happen when this bridge is widened. At a bigger value for L, only the resonance should happen for this frequency. So let's anyway start from this point. Keep this bridge at the same point for the previous one. You can see there is a very small vibration. It doesn't mean that high energy is transferred. Let me increase the wavelength now, the gap between the bridges. Still, that's not the highest. Increase little by little, little by little. You can see the vibration increases. Let's keep it closer to the midpoint of these bridges. The vibration increases. Let's increase the gap a little bit more. You can see one was thrown out. One was thrown out. Let me keep it again. Let me keep the paper riders again. Try it again. See, like when I am hitting with this hammer, there might be a wind flow. Because of that also it might flow. You must make sure it doesn't flow because of that. After you keep it here, because of the vibration, the paper rider should be thrown out. You can see both were thrown out, which means this is the point where maximum energy is being transferred from the tuning fork to the sonometer, which means the resonance is happening. Let me take the readings now. This is 53. I didn't change that. The other end, it is at 39.5, 39.5. 53, 39. This is for 384 hertz. 384 hertz I used. 53 and this side is 39.5. That means 13.5 centimeters gap I am getting. 13.5 centimeters gap. Lambda by 2 is going to be 13.5 centimeters. Now what do we do? I did this for 384 hertz. Let me keep it. Take the next lower frequency. The next one is 341. I have 341.3 hertz. Let me place the paper riders again. Let's keep these paper riders again. Right. So since I am using a lower frequency, the lambda has to be even more. Anyway, let's start from the previous point and start widening it. Small vibration is there. Increase it. Still not the highest energy transfer is here. Still not. You can see it vibrates more, but not to a level of being thrown out. Increase it further. Increase it. More vibration. Maybe I can increase a little bit more in millimeters. The vibration increases, but not to the level of being thrown out. Not enough. It starts to reduce again. The vibration reduces, which means I have missed the resonance points. Let's come back. Let's come back. Let's start from here again. Seems like I missed the resonance point. Not enough. Let's increase little by little. Not enough. You can see at this point the vibration seems to be high. Let me try it once again. Let me keep it again. We saw one was thrown out. Let me keep the paper rider again. Keep it somewhere in the middle of this bridge so that it experiences the displacement of amplitude. You can see the vibration is much higher. Yes, you can see it's being thrown out. One of those pieces were thrown out. One of those riders were thrown out, which means this is where the resonance happened. You saw it clearly. Before this point, the resonance did not happen. The paper rider was not thrown out. After this point, it was not thrown out. This is the point where the paper rider was being thrown out, which means this is where the resonance happens. So lambda by 2 has to be equal to this length. This is kept at 53, and the reading here I have 38 centimeters, 38 centimeters. So 53, 38, we get 15 centimeters. This is for 341.3 hertz. 341.3 hertz. This was anyway at 53. The other side reading is at 38 centimeter, 38 centimeter, and the gap is 15 centimeter, 15 centimeters, right? So that's the third frequency that I have used. Third frequency I have used. Let me take the fourth one now. After 341, what do we have? We have 320 hertz is there. Let's place this paper rider again. Start from the beginning again. No, it's not the highest. Let me increase a little bit. Let's see. No, not the maximum. No, no. You can see the paper riders are vibrating, but not as much as to be a level of being thrown out. We can see more vibration now. Maybe I can increase a little bit more and see. Keep it in the middle. Yes, that's being thrown out there. Shall we check again? Thing is this, when you are keeping this tuning fork here, you must ensure none of your body part touches the resonance box, because then what will happen, the sonometer box, because when what will happen if your body part touches it, then energy will be transferred to your body as well. So the energy transferred to this string will be less. So make sure when you keep it like this, none of your body part touches this. Then only you can observe the vibration as much as possible. Let's see again. Can you see? Both pieces were thrown out. After I kept it here, because of the vibration, both were thrown out. Let's check the readings now. 53. This is at 36.8. 36, but this is for 320 hertz. 320 hertz. This is at 36.8 centimeters. So the difference we get is 16.2 centimeters. 16.2. 16.2 centimeters difference we are getting. Lambda by 2 is going to be 16.2 centimeters. Now let me take the last one. Last one. Last one. This is 256 hertz. Place the paper riders again. 320 to 256, that's a huge drop of frequency. You can expect the length to increase by quite some amount. Let me start from the same gap, but I can expect a much bigger length than this. No, not much of energy had been transferred to the paper riders. No, I can't see much of a vibration there. Still not. I told you 320 to 256, there is a huge drop, huge drop. Still no, let me keep it in the middle. Increases a little bit more. You can see, maybe I can reduce it a little bit and check again. High level of vibration happens. Let's confirm the point. Still not the perfect point. Let me increase a little bit more. Though it has reduced, that means I have passed the point where the resonance happens. Come inside further. Okay, let me check at this point. Seems like that is the point. Can you see? The vibration is much higher. So the gap for that is, the length is 53 and here it is 33. So 53 to 33, 20 centimeters we are getting, 20 centimeters. 256 hertz we get 20 centimeters, right? So we have got 5 different length readings for 5 different frequencies. As I mentioned earlier, we can draw a graph against 1 over f and L, and we can find the gradient of the graph. From the gradient, we can find the velocity of this transverse wave. There is one more thing I have to mention here. As I mentioned earlier, you can connect this string above this pulley. You can connect it above the pulley, and you can hang different weights there, right? You can hang it there, you can put different weights there, and you can change the tension on this string. Okay. Then we can do another experiment on this, how the tension and the L changes. When the tension changes, maybe for the same frequency, let's say for 256 centimeter itself, when the tension changes, how this L changes, you can do another experiment as well. It's all the same procedure, only difference is going to be here this time we change the frequencies. Next time if you are doing like that, you are not going to change the frequency, you will be changing the weight that you are connecting there, so that the tension changes. When the tension changes, what happens to the length, we can do as a separate experiment. Right. So, since it is the same procedures again, I am not repeating the same experiment, but you can even do calculations. When I do past paper questions on this area, I will show you questions on that type as well. Right. So, now let's write down all these values on a table. 426.6 hertz, we got 12 centimeters. 426.6, we got 12 centimeters. 384 hertz, we got 13 centimeter. 384 hertz, 13. 341.3 hertz, we got 15 centimeters. 341.3 hertz, we got 15 centimeters. 320 hertz, we got 16 centimeters. 320, we got 16 centimeters, and 256 hertz, we got 20 centimeters. 256 hertz, we got 20 centimeters. With these values, let's draw the graph. Right, we are expecting y equals mx graph. From the graph, we will measure the gradient. Using the gradient, let's see if we can find the velocity or speed of the transverse wave along the stretched string that we have used here.
Dear students, now let's see another experiment in physics in the section mechanics. What we are going to do here, we are going to arrange a pendulum, simple pendulum, and using the pendulum, we are going to find the gravitational acceleration. We usually mark it as g, gravitational acceleration g, simple g, and the value of that we always take it as 9.8 or 10 meter per second squared. That we already know the value and we use that in calculations, but how to derive that value experimentally is what we are going to see now, right. So, look at this, when I say pendulum, right. So, look at this, a string ball here, right. What do? You give a small displacement horizontally, then it will start oscillating. How does it oscillate? Let me show it to you. Right, it oscillates like this by a small angle. Don't oscillate it by like 30-40 degrees, must be like 5, 6, 7 degrees in that range. A small oscillation, small displacement has to be given by the time for one full oscillation. One full oscillation means, see, it starts from here, it goes up to here and then return and again it goes up. So, starting from 1, 2, 3, coming back here 4. 1, 2, 3, 4 is what you call one full oscillation. From the middle it goes to the right side, comes back to the left side, again it goes to the middle, that is one full oscillation we say. And the time for that oscillation t is given by 2 pi square root of L over G. 2 pi square root of L over G. L is the length of pendulum, G is the gravitational acceleration that we want to find. So, it is very simple, you can see, you measure the length and let it oscillate and find the time for oscillation.
T is known, L is known, you can find G. But in physics, we usually go for the graphical method. So, if you are going to use a graphical method, what do? Square this, T squared, 2 pi getting squared, it will be 4 pi squared. G comes out and L also comes out. Y, M, X. We are going to change the length of this pendulum to multiple different values, one by one. You change it, maybe like take 50 centimeter, 100 centimeter, 150 centimeter, likewise. Take different lengths and measure the time and draw the graph T squared versus L. T squared versus L. The gradient of that graph has to give you 4 pi squared over G. Then G will be 4 pi squared over gradient. This is what we are going to do. Right? Simple. Few things that you have to note here. One, when you measure L, the length has to be measured from the center of this ball, because pendulum, not only the string, even maybe if you know the length of the string, then you have to add the radius of this ball, so that will be the total length. That is what we mark as L. Basically, length has to be measured from the center of gravity of the ball that we use here. Since we usually use a uniform sphere, you can take the center as the center of gravity. Right? So, with the length of string, radius of that ball has to be added to find the total length of pendulum. Point number 1. Point number 2, okay, how are we going to fix this on the top? If you take a stand and if you fix it with a clamp, say this is your stand, then you have a clamp here, right. Here if I hang this, what will happen? Let me show you the view from this side. If I look it from this side, how it will look like. This clamp will have a shape. Let us say it has a shape like cross section is circular and the string will come like this. Right. Now, let us consider different positions when it swings. When it swings, okay, this is one position. This is another position, right. I will draw even more enlarged here. What will happen? Enlarged. Once you have it like this, another position you have it like this, another position you have it like this. So, what is the problem with this? Length of pendulum changes according to the position. Can you see? When it is at this position, you are going to measure the length from here. Why? From there it oscillates. When the pendulum is at this position, the length starts from here. When the pendulum is at this position, the length starts from here. So, it is not appropriate to rotate that, to rotate the or to coil that that we got on a table. L, these are the L values we have used, and time for 20 oscillations we have marked. Then I divided each of them by 20 and I got T, oscillation time for one oscillation, 20, 54 by 20 is 2.7, 50 by 20 is 2.5, 2.25 to 1.75. And I squared that as well, because you remember I explained T equals 2 pi square root of L over G. So, T squared is what we take in the y axis, 4 pi squared over G into L. This is what we take in the y axis, y equals mx. Yeah. So, T squared, each of those values I have squared and I have got these values. Now, we need to draw the graph. Draw the graph.
Let us draw the axis. This is going to be t squared second squared. This is L in centimeters. L you need up to 175. 175. So that's like let's say we'll put 25. 100 we got 4. The last one. Oh, this was 75, not 50, 75, right? 75, 3.06. 75, 3.06. 75, 3.06. Here. That's it. Those are the values we have got. We are expecting a line through origin. Let's see if we get that. Right, that's how the graph is going to be. Am I right? Check that. Yes, that's how we get it. Students, let's see the past paper questions on this experiment. This is from 2006 paper. A student plans to find the acceleration. Pendulum's length is L, right? It rotates through angle theta towards that side. They mark 2 points as A and B. Let's see what it is about. Write down an expression for the period of oscillations t of the simple pendulum in terms of the length L of the pendulum and the acceleration due to gravity. We all know that that's a giveaway question, so simple, 2 pi square root of L over G. 1 mark, so easy, got it. Rearrange the above expression in the most suitable manner in order to obtain a value of for G by plotting the graph. Again, another simple one, t squared is going to be 4 pi squared over G into L. This is going to be Y, this is going to be X, this will be M. When taking readings for T, the student keeps reference pin directed at the point B as shown in the above diagram. State why directing of this pin at B gives a better accuracy for the time measurement than directing at point A. So whether you are going to keep the pin here, he said student has decided to keep it at B. B is the lowest point, see. So why do we keep it at the lowest point, not anywhere else? This is where the speed will be high. So see, like the pin is going to be like this. When the thread passes it very fast, then the error will be less there, right? Imagine if the pin moves very slowly, to pass the pin itself it's going to take some seconds, right? Say half of the second it takes. Then at which point you assume as it passes the point? Imagine if the pin is, if the thread is too small, too slow, if the pendulum is too slow, to pass the pin it takes some time. So whether at the beginning of passing it or at the end of passing it, when are you going to take it as passing the point can be a confusion. But when the pin is here, if the pendulum passes it very fast, the time it takes just to pass this pin is minimized. Time that takes to pass the pin is minimized. That's why we always prefer keeping it at the lowest point, because the speed is high. Pendulum speed will be high. Yes. So we can say at B, the speed will be highest. That to cross the pin or pass the pin is minimized, is lowest. It's the lowest. This is the lowest. When the student measured the time for only one oscillation, his reading was 2 seconds. If the instrumental error in time is 0.1 second, determine the percentage error value of the period of oscillations. 2.1 into 100. They said percentage oscillation percentage. Instead of measuring the time for one oscillation, he measured the time for 25 oscillations and the value obtained was 50.2 seconds. Determine the percentage error of the value of the time measurement. See, basic stuff they are asking. Basic stuff. So, it's going to be 10 divided by 50.2. 1. Then you get 498. So, this is going to be 9.19. Yeah. So, they say to the nearest first decimal place, we can give it as 0.2. 0.2 percentage. 0.2 percentage. The student used a uniform metal sphere of radius r as a pendulum bob. After plotting the t squared versus L graph, he found that the gradient was 4 and the intercept was 0.04. Right. Rewrite the expression in part A in terms of L and R. Now look at this. Look at this. The pendulum's length is going to be this much. So, what we used as L is actually capital L plus R. So, t squared equals 4 pi squared over g into L. Instead of L, now I am going to write L plus R because capital L is the length of the string only and R is the radius of the sphere. Remember, I told you the length of pendulum has to be measured from the center of the sphere. So, L plus R has to be the length of pendulum. Right. Rewrite the expression in part A in terms of L and R. Determine G. So, now look at this. T squared 4 pi squared over G into L plus 4 pi squared R over G. This is 1, this is Y, this is X, M and C. So, anyway the gradient is 4 pi squared over G. They have given the value of gradient is 4. Gradient is 4. Gradient 4 pi squared over G is 4. So, G is pi squared, which is approximately 10. Which is approximately, they said take pi as 3.1, wait. 3.1 squared, 31, 93, 961. 9.61 ms minus 2. 9.61 ms minus 2 is what you get. Careful, they said take pi as 3.1. Next, determine the radius r of the sphere. R is going to be, look at this. See, here you have 4 pi squared over G, here you have 4 pi squared G. Friends, let us see the past paper questions on this experiment. This is from 2006 paper. A student plans to find the acceleration due to gravity in the laboratory using a simple pendulum. They have given an image here. Pendulum's length is L, right? It rotates through angle theta towards that side. They mark 2 points as A and B. Let us see what it is about. Write down an expression for the period of oscillations t of the simple pendulum in terms of the length L of the pendulum and the acceleration due to gravity. We all know that that's a giveaway question, so simple, 2 pi square root of L over G. 1 mark, so easy, got it. Rearrange the above expression in the most suitable manner in order to obtain a value of for G by plotting the graph. Again, another simple one. T squared is going to be 4 pi squared over G into L. This is going to be Y, this is going to be X, this will be M. When taking readings for T, the student keeps reference pin directed at the point B as shown in the above diagram. State why directing of this pin at B gives a better accuracy for the time measurement than directing at point A. So whether you are going to keep the pin here or here is the discussion. He said student has decided to keep it at B. B is the lowest point. See. So why do we keep it at the lowest point, not anywhere else? This is where the speed will be high. So see, like the pin is going to be like this. When the thread passes it very fast, then the error will be less there, right? Imagine if the pin moves very slowly, to pass the pin itself, it's going to take some seconds, right? Say half of the second it takes. Which point you assume as it passes the point? Imagine if the pin is, if the thread is too small, too slow, if the pendulum is too slow, to pass the pin it takes some time. So whether at the beginning of passing it or at the end of passing it, when are you going to take it as passing the point can be a confusion. But when the pin is here, if the pendulum passes it very fast, the time it takes just to pass this pin is minimized. Time that takes to pass the pin is minimized. That's why we always prefer keeping it at the lowest point, because the speed is high. Pendulum speed will be high. Yes. So we can say at B, the speed will be highest. The time to cross the pin or pass the pin is minimized, is lowest. It's the lowest. This is the lowest. When the student measured the time for only one oscillation, his reading was 2 seconds. If the instrumental error in time is 0.1 second, determine the percentage error value of the period of oscillations. 2.1 into 100. They said percentage oscillation, right? So it's going to be 10 by 2, 5%. 5%. Instead of measuring the time for one oscillation, he measured the time for 25 oscillations and the value obtained was 50.2 seconds. Determine the percentage error of the value of the time measurement. See, basic stuff there. Right, this is another question. This is from 2015 paper. Figure 1 shows the motion of a simple pendulum of length L. Write down an expression for the period of oscillation T of the simple pendulum in terms of L and acceleration due to gravity G. That is simple. T equals 2 pi square root of L over G. Alright. If the laboratory experiment to find the value of G using the simple pendulum, you are provided with a stopwatch which can measure the time with an accuracy of 0.5 seconds. If the estimated value of the period T is 2 seconds, determine the maximum number of oscillations you should take to reduce the percentage error of T down to 1%. Alright, let's see. If you want to reduce it to 1%, 0.5, 2 into n number of oscillations, it must be 1%. Yep. So, percentage multiplied by 100. See, this is the error, this is the measurement we take, 2 seconds into number of oscillations into 100. This has to be 1%. So, this is 50 by 2, n is 25. So, if you take for 25 oscillations, then you can have the percentage error to be 1%. A student has designed an electrical method to determine the period of oscillation T more accurately by using a detector system. So, this is where he has a source diode. This is where he has the detector. It looks like a small magnetic thing. When the pendulum passes a ray, IR beam, infrared beam goes to the detector. When the pendulum crosses this beam, the signal is going to be disconnected, right? the receiver detector will not receive that signal. Right. So, let us see what he does. The detector system consists of a source diode and a detector diode. Source diode emits a narrow beam of infrared light with a constant intensity of L naught. This light beam is detected by the detector diode and it also measures the intensity of the beam. Detector system is placed in the path of the bob of the simple pendulum. While oscillating, the bob also crosses the IR beam. Whenever the bob interrupts the IR beam, the detector diode signal becomes 0. Otherwise, it produces a signal of constant L naught. When the bob is oscillating, the computer monitor displays a graph of the value variation of the detector signal intensity L and I. So, simply what happens, always see, like if there is no pendulum, the detector will continuously receive the infrared beam, the signal will be continuously there. But now what is going to happen when the pendulum crosses it time to time, you will have like this, signal comes, then when the pendulum crosses it, you do not have signal, again crosses it, again signal, crosses it, likewise it goes, right. Understand, it is very simple. If the pendulum does not cross, then it will always be the signal like this. When pendulum crosses it, for the pendulum bob to pass that IR ray, it takes a while, right. Within that time gap, there is no signal, it is 0. Figure 3 shows such a graph, here you go, displayed on the computer screen, and it is taken in a situation where the force due to air drag is negligible. Air drag is negligible. The time interval corresponding to the 0 detector signal is T0. This gap is T0, T0, T0. Value of T naught depends on the speed V with the bob crosses the when the bob crosses the IR beam and the diameter D of the bob. Yes, because see, this is how the bob is going to be, right. So, if the IR beam is at this point, the time it is going to take D divided by V. D is this distance. So, entire distance has to finish passing the IR ray. Velocity is V. D divided by V will give you the time. What will happen to the value of T naught when V is increased? When V is increased, it will pass quickly, right. So, T naught will reduce. T naught reduces. Related to D, when D is increased, T naught also will increase. Because you are using a bigger bob, it will take more time to pass that beam. T naught increases. T naught increases. Write down an expression to estimate V in terms of D and T naught. Yes. So, V is going to be the distance divided by time, D over T naught. What is the value of T according to the graph given below in figure 3? T means the oscillation time. Look at this. Now see the beam, let us say the beam is going perpendicular to this plane. Okay. The pendulum goes here, comes back and comes back. This is what you call one full oscillation is. So, when it goes rightwards, it first let us say this is where number 1, number 2, number 3 again is going to cross it. So, this is where number 3 is 1, 2, 3, 4, 5. That is how one full oscillation is going to be. 5 will be at this point. Or if I name it as A, B, C, D, E, look at this again. Numbers can be sometimes confusing. Okay. Let us say when it starts, this point is A, that is here A, B, C. When it returns, this point is C, that is going to be here C. And again it returns to the initial position E. E is here. So, one full oscillation means from here A to E is what you call one full oscillation. It takes 3 seconds. Can you see? 3 seconds from 0 to 3 seconds. So, T is 3 seconds. Where is that? 3 seconds. Student, place the detector system at the most appropriate position of the path of the bob to determine the maximum speed Vm of the bob and obtained a graph similar to the graph shown in figure 3. With respect to figure 1 above, given the position A or B at which the student should keep the detector system in order to determine V maximum. V maximum is at the lowest point only. The velocity will be maximum for a pendulum at the lowest point. Give the reason for your choice. Let's see where they have marked AB. Where is the pendulum? AB. A is the lowest point. That is where the Vm velocity is maximum. So, he has to place the detector system at point A. Point A. So, A, the speed of the bob, is maximum at its lowest point. Because what happens when it goes up and up, the potential energy increases. So, the kinetic energy reduces. So, when it goes up and up, the velocity reduces. When it comes down, potential energy reduces because height reduces. So, kinetic energy increases. How can the kinetic energy increase? Velocity can increase. In order to carry out this experiment, the student says that the cylindrical bob shown in figure 4a is better than the spherical bob shown in figure 4b. If both bobs have same diameter d, give a reason to justify his statement. Imagine now the beam goes like this. Now, if your beam is like this is how we have to exactly set it up if you are using a spherical beam. But the problem is, in daylight, the infrared ray will not be visible to us. We will not be able to see the infrared ray. Then, how do we know whether it passes through the diameter itself? What happens if it is like this? What happens if it is like this? Still in the monitor, when you observe the signal, you will see the monitor gets stopped, because when this part passes the infrared ray, anyway the signal gets disconnected. But you wouldn't know whether it is through the diameter or not. Actually, if this is the case, if this is how the arrangement is made, it is not passing through the diameter. This gap is going to be something else. This is not D. Understand? So, since infrared rays may not be visible to bare eyes, you won't be able to ensure that the ray goes through the diameter of the spherical bob. But if it is a cylindrical bob, wherever it passes doesn't matter, right? See, if the beam is like this, still it has to cut the distance of D. Here D, here D. So, wherever it cuts, it has to anyway cut the distance D. That's why he said this is better than that. So, he is asking now, what is the question on us? If both bobs have the same diameter D, give a reason to justify his statement. Okay. So, let us say the IR ray may not be visible. When we use spherical bob, it is difficult to ensure that the ray passes through the diameter of the bob. If cylindrical bob is used, this issue doesn't arise. this issue doesn't arise. The student decided to calculate Vm using the graph mentioned above and the expression in C2. Can he get exact value for Vm by this method? Explain your answer. Graph method and the expression C2. Now, the problem is, now see, since there is going to be R track and all, okay, if you take the point here, it's just an instantaneous speed. We can't say that is going to be the V maximum always. After a couple of oscillations, it can be a different value, right? So, when you count 25 oscillations, each oscillation, the velocity maximum velocity could be different. So, what you would measure from this might be an instantaneous value, not the average value, right? So, let us mention that. Know what is measured from the graph is an instantaneous value. Instantaneous value is an instantaneous value. The student observed that in a situation where the force due to air drag is significant, the maximum speed Vm that be obtained decreases considerably from oscillation to oscillation and the bob finally comes to rest. For such a situation, complete the graph I with t that you would expect for a period time t on the figure, right. So, what he says is air drag is significant. So, first time it passes faster, second time it is going to be slower than the first time, third time it is going to be even slower. So, what will happen, that time t naught will increase because it passes slowly. So, now look at the graph how it is going to be. Let us put the vertical lines first. Okay, let us say, oh, t is here. T 0, yes. Correct. That is how the graph is going to be. What do we know? Time gap here and time gap here. Can you see? This must be bigger. It takes more time than the previous time because it started going slowly. If the maximum speed of the bob at t equals 0 and t equals t are 0.44 meter per second squared per second and 0.42 meter per second. Simple m has to be 2 into, this must be 10 to the power minus 3, 2 into 10 to the power minus 3 into gradient. Gradient we got 0.04. We need to solve this nicely now. Let us see how we can solve it. 0.5 and 2 will be 0.25. I will keep it 0.25 itself because f squared, when I take f, I have to take the square root, isn't it? 10 to the power minus 3 and this 10 will become 10 to the power 4. 4 and 0.04 is 0.16. 0.16. Take the square root both sides, f is going to be, this will be 0.5, this will be 10 squared, this is 0.4. So, that is 50 by 0.4 which is 125. You get 125 hertz, Clear? Right. So, that is another question on this experiment that was tested in 2009 paper. Right, it was not that difficult, we had some extra calculations there, but that is all from 2009. I already did 2005 paper, I did 2009 paper, now let us see another paper. 2017. You are asked to determine the mass per unit length of a given wire by taking only one measurement using a sonometer and a tuning fork.
Figure shows a standard sonometer setup used in a school laboratory fixed with a given wire. The wire is stretched with a tension T between two bridges A and B. In this setup, the bridge A is fixed and bridge B is allowed. A is fixed and B is allowed to move. The tension in wire could be changed by varying the load mass M. A tuning fork with known frequency F is provided to you. Right, look at this. This is the arrangement. I told you, like, okay, if you want to change the tension, this is what we do. We bring the wire, bring it over a pulley and fix a mass there. And you are given additional masses also. So, if you want, you can increase the masses here. A, B are the bridges. So, by A is fixed, B can be moved. What type of vibrations is provided in the surrounding air due to the vibration of a tuning fork in this experiment? In the surrounding air, what you get is longitudinal waves. If m is the mass per unit length of the stretched wire of tension T, write down an expression for the speed V of transverse waves on the wire in terms of T and m. We studied that multiple times. In this experiment, you are supposed to measure the resonant length L of the wire resonating with the tuning fork at the fundamental note. A student suggested that there can be three ways A, B and C of keeping a vibrated tuning fork to obtain the resonant state as shown in figure. A, B, C. You know these two are wrong, right? We have to keep it such that the tuning fork is kept on the sonometer box, not above the sonometer box, not close to the wire. It must be kept on the box. So, this is what is right. XY represents a part of surface of the sonometer box. A, tuning fork held normal to XY and touching XY. B, tuning fork held normal to XY and without touching XY. C, tuning fork held above the stretched wire. In order to obtain a maximum amplitude for resonance out of the above three ways, which way would you select to keep the vibrated tuning fork? A, B or C? It was A, right? It was A. Give reason for your selection. What will happen? See, when you keep it like this, the vibration will first go to the air here. Then only it gets transferred to the box. So, the energy transferred to the box will be minimum because a lot of energy is going to be taken by the air particles in between. So, from the tuning fork to the sonometer, the energy transfer will not be maximized. Same problem there. This is where directly from the tuning fork, energy is going to be transferred to the sonometer box. So, they are asking you to give the reasons also. Give reasons for your selection. To maximize the energy transfer, to sonometer from tuning fork. Write down the other item that you normally use in this experiment to detect the resonance state experimentally. What is the other item we need here? We need a paper rider, right? You need a paper rider that we keep it on the spring, on the wire, and it gets thrown out when the resonance takes place. Write down the main experimental steps you follow to detect the optimum resonance state. The usual one we have written in the previous question also, 2009 also they asked. What do? Keep A and B at minimal gap. Place the paper rider on the string or on the wire in between or in the middle of A and B. In the middle of A and B.
vibrate the tuning fork and keep it on the sonometer box. Increase, or let's say move B to increase the gap between A and B until the paper rider is thrown out. Until the paper rider is thrown out. So, when it is thrown out, the resonance is confirmed. At this instance, the resonance takes place. At this instance, the resonance takes place. Next, obtain an expression for M in terms of F, L and T. Simple, V equals F lambda. They say obtain, so you have to show the steps. V is square root of T over M. F lambda will be 2L. 2L. So, they ask you to find M, right? So, T over M equals 4F squared L squared. M is going to be T over 4F squared L squared. Correct? If the resonant length that you have obtained in this experiment is small, how do you adjust the above sonometer setup in a suitable manner to obtain a reasonably large resonant length for the given tuning fork? Repeat, if the resonant length that you have obtained in this experiment is small, how do you adjust the above sonometer setup in a suitable manner? Now, look at this. L is equal to, let's make L the subject of it. L is equal to 1 over 2F square root of T over M. For the given tuning fork, which means F cannot be changed, F is constant, frequency is constant. But you need a bigger length, L has to be increased. What can we do? You can increase the tension. You can increase the tension, right? They are positively correlated. If T increases, L also will increase. We can say, have they given the name for that? Let's see. We can say additional masses can be added with capital M and increase the tension. Additional masses can be added to M and increase T. When M is 3.2 kilogram, F is 320 hertz, the resonant length was found to be 25 centimeter. Find the mass per unit length of the wire in kilogram per meter. Right. M, the formula we have T over 4F squared L squared. T over 4F squared L squared. T is going to be 32. 4 F squared has to be 320 squared into L squared has to be 320 squared. Let's write as 320 into 320. Right. L squared 25 squared. We have to solve this and get the answer. Let's solve it carefully. Wait, this is in centimeters, right? Then I can put 10 to the power minus 4 because 10 to the power minus 2 to convert it to meter. There is squared, so that makes it 10 to the power minus 4. 10. Now look at this. this 10, this 10, and I'll take another 100 from here. 4 into 25 is 100, right? That 100 and these two zeros will cancel this, correct? Then what you have is 1 over 32 into 25. 32 into 25, if you take a 4 out of it, it's going to be 100. If I write it as 8 into 4, that 4 will make the 25 100. So, I can say what you have is 1 over 800 kilogram meter minus 1. That is, if I take it as 1000, 1.25 into 10 to the power minus 3 kilogram meter minus 1. Right. So, you have to be a bit careful with the calculations, rather than multiplying, dividing everything directly, you must find some shortcuts to get rid of it. See, 32, 32, anyway, you know that. Then 4 and 25 makes it 100, right. So, you don't have to write 25 into 25, 625, you don't have to go into all that. 4 into 25 is 100. Those two zeros, 1 0 here, 1 0 here, 4 zeros will cancel this into the power minus 4. So, you need to have some, techniques like that to solve it simply and get the answer. Right. If you had been following all what I was doing, in each calculation I show you different techniques. Right. So, you can learn techniques, and then when you practice, you can come up with your own techniques to solve things quickly. There is no standard way of solving things quickly. In each case, you have to find out a quicker way of solving it. Right. Then only you can save some time in the exam. So, that's all the past paper questions from this experiment. I have done 3 past paper questions for you, 2005, 2009 and 2017. Practice all this, right. There is nothing difficult in this. It is quite an easy, straightforward experiment. You should be able to answer any question that you get in your exams. Next, after this, we will see another experiment in physics in the next session.